How's it going, everyone? Eulier Gonzalez here, looking right now at the LeetCode problem solutions as a way to understand these computer science tools and develop a pattern recognition when it comes to solve common problems with common data structure and algorithm, whether it is arrays and hashing, and then using now algorithms like two pointers, sliding windows, binary search, and then using another data structure like stack in combination with arrays and hashing, as well as the linked list, and ultimately to understand trees, tries, heap priority queues, and backtracking. Again, this is only to reach at what? To reach to only at that particular level, because then you have this more advanced topic like intervals, greedy, advanced graph. I think they update that. Graph, 1DP, 2D, TB, bit manipulation, match geometry. But you get the idea. The idea here is that start with the basics, okay, and reach until this point, the trees. That's quite interesting. Yep, that's quite interesting. As a way to now build our knowledge and then understand that, right? So, right now we're looking is at the arrays and the arrays and hashing, and how by looking at the easiest one as a way to, hey, how you want to see if this contains duplicate. You can work with sets for that. How you want to check if there is a valid anagram as a way to sort these kind of elements. Hey, how you can make sure that the two sum, how you can identify is the index of two sums elements here. So by having a hash map, and then you say, all right, I'm going to now in our hash map store the index as a value and the key as the array value, or the number value here. And if I find that key as a result of the difference, meaning when I iterate through this number of elements, if I get this number and then I subtract with the target, and if that actually match with what we already have in our hash as a key, please give me the index of that. But the idea here is to see how we can play now with arithmetic and hashes, something that we also do here with group anagrams as a way to say, hey, now how you can group anagrams with using a hash table in an array of anagrams, okay, or an array of words. So by using is the hash as a way to say, hey, I'm gonna store is as the key that sorted word, and if that doesn't exist, I'm going to append that, okay. However, if that exists, if that sorted word exists, then now let me is store that as a value. And if I actually find a sorted word that actually match our index, our sorted word in our hash, as we iterate through all of these elements, please add those values in our hash map. So here we are playing is with hash maps and arrays. So now we're talking about is the TK frequent elements. And that'll be something interesting. So they have this solution here in Python, but I will use is now JavaScript, or specifically TypeScript for that. All right, here we go. Top key frequent elements. Giving an integer array nums and an integer key, return the most frequent elements. You may return the answer in any order. So if we read at the input here is this, okay? And then you say, and an integer k, return the k most frequent elements. What k represents? Return the k most frequent elements. Return the key most frequent elements. Okay. Okay. This is now the k most frequent elements. All right. Okay. So those elements are that at least have 2 or more. Please return me those values in this order. All right. Makes sense. So the constraint is that 1 is minor or equal to the number dot length, like so. Okay. The length will be is for negative number and positive numbers. That's interesting. And the key is the range in which 1 is 1 or the number of unique elements in the array. So it is guaranteed that the answer is unique. Follow up, your algorithm complexity must be better than n log n, where n is the array size. So our intuition here. So the intuition is that we need to store somehow which of these elements do we have, okay, by saying is we need, let me actually do this. This is the intuition. So we need to count the number of times we need to count the number of times a number in the nums. Okay, so we need to count the number of times a number in the nums are starting exactly are, okay, and then somehow only return as an array those numbers whose counter those number whose counter are greater are equal or greater than the k target. That's the intuition. So what will be the approach? So that makes a lot of sense. So we need to find somehow is to count all of this number and how many times those numbers in these collections are. Okay, we're gonna count that, and then we're gonna decide is in our hash map which one of them or in our hash which one of them actually is greater than the k target, right? And then return that as an array. So the approach here might be something like iterate through the array. Okay, so define a hash. Let me recap my logic here. So we need to count the number of times. So we need to count is the number of times that number actually occur or the number of occurrence of that number in our collection. Okay, and the way we can do that is by having is a key as number of. We can do that. We can have is the key to store is the number, and as a value is the counter. You know, so because after all, we would like is to is return is what are the elements that satisfy is the most high k elements, the most k frequent. Okay, when we're doing that, when we are now adding that elements, when we are counting that elements, we can say, hey, is this, we can make is a check here, is this number actually is equal or greater than the k target? Please, let's go to add that to a result. So we need to define is a hash to count our numbers occurrence. Okay, I think I write it good. Exactly, our numbers occurrence. Okay, to define a hash to count our numbers occurrence, define an array to push all the numbers that all the number that all the numbers all yeah define an array to push all matches numbers. Define an array to push all matches numbers. Yeah, define an array to push all k matches number. Okay, define an array to push all the k matches number. Okay, and then iterate through the array. All right, where we're going to count. So as we iterate through the array, let's go. So let's check if that number exists in our hash. If it is, if it's not, add it with the value of 0. If it is, okay, if it is, add the value +1. Okay, and also let's go to actually check after that. Okay, let's go to actually check exactly. Let's check if that number, and let's check the value of our number. Okay, let's check the value, or let's check the counter. Let's check the counter in our hash. Okay, of that number. Okay, let's check the counter in our hash of that number. If that is greater, if that is equal to k, then add such number to the matches k numbers. Okay, and then return. Yeah, and then return the matches que numbers array. Pretty much is that. So that is our approach. Okay? So this in theory is supposed to work. And this is pseudocode. This in theory is supposed to work. Now let's do this. Let's get into this. But it all starts with an intuition. Okay? And then how are we going to approach to this? So because we already have experience to that, so first define a hash to count our numbers occurrence, and that is this will call, let's gonna call is the counts hash counter, or you can say dictionary counter if you come from Python. Okay, hey, this will be a new map object. Okay, also let me define is the matches, which will be is a new array empty, and then it's going to iterate through this using now is the iterable approach, the iterative protocol, which is now using is the nums.entries, which is entries comes from the array, that is indicating is that, hey, this let's going to return a, as you can see here, the entry methods of array instance return a new array iterator object that contains the key value pair for each index. And when you say array iterator, it returns this iterator object that conforms to the iterator protocol, you know, which is let me close this. Here we are. That's right. Okay. Which is this. So instead of actually us being imperative by using is a for loop, and then you say let define is the index, instead of actually us having to define this in an imperative way, let's going to use is the iteration protocol. Why is that? Because now this is the way of how you can, most of the time we don't care about how we're going to access the data. We just only care that we get the data that we need, and then we're gonna do something about it. So this is this descriptive nature of how you want to do the things, instead of this descriptive nature in say what do you want to do instead of how do you want to do, is something that is the community is pushing forward, because now it actually focuses our attention on what really is, what really matters here. And what really matters is that working with the data. So we can go with the imperative approach. There's nothing wrong with that. But we also can is now uses the iterative, which any array have these methods called entries that it returns an iterator. The return is a new array iterator, okay? And the iterator is just an object that conform to the iterator protocol. And the iterator protocol is just one of the two in the iterator protocol is one of the two pieces of the iteration protocol as a way to now implement those following this convention. The iterable protocol, where this allows you to customize the behavior or the iteration behavior using is the for of loop, okay? By actually now, when you're gonna use behind the scene is the object, by putting is the symbol .iterator, you can now indicate to this object how it's going to behave, what will be this iterative nature of that. That's quite interesting. And this is the iterable protocol. This is how it's going to behave. This is how you can define customize the iteration behavior when it's going to be used with the for of loop. But also, you need to also satisfy the another piece of this iterative protocol or the iteration protocol, which is the iterator, the way of how you're going to produce all of this sequence of elements as your define an iterable or an iteration behavior. And this iteration protocol, which is what is return this entries, it returns a new array iterator object that satisfy this condition, which is this is an object that is going to return that contains the next, which is a function that has the value and the DOM properties, okay? And you also have is the return and the throw, all right? Function, but at least must have is the next. So anytime the for of loop, okay, anytime the for of loop calls this, okay, so anytime the for of loop calls this, you will get is the key and the values, in our case is number, all right? And from there, what you're gonna do is this. Now, because we started to iterate through that, the for of loop is going to behind the scenes call this next methods as a way to say, hey, please provide me is the first element, and then call this next method again, provide me the second element, and then the third element, and so on until there is no more elements to that. That's very interesting, because this is also this is what Python is using behind the scenes, this particularly design method, or this design pattern, the iterator protocol, as a way to now being able to traverse to a data structure regardless how it was implemented, you know? All right, so in any case, but if we follow this, iterate through the array, let's check if the number exists in our array. In this case is like, let's say if that number exists in our array, which is dictionary counter has that number. Okay, do we have that? If we don't have that, please let's go into add it. Okay, let's go into add it. Let's go into add it. Okay, let's go into add it. How do we add this? Let's go to add this. You had set that number with a counter of 0 initially. Okay. However, if we have that, otherwise, if that exists, so let me now update the dictionary value there, which is update the counter there. Dictionary counter dot set of the number, and here we're gonna get the dictionary value. Okay, yeah, the dictionary counter dot get as a number. Okay, so we are now getting is the value from our hash map, and then add +1. All right, and also because we already now count that, I just want us to check that. So let me actually do something much more readable, which is say counter increase counter. Okay, like this. Say increase counter. All right. So now that we increase the counter, I want you to actually see what is the value of it. Instead of here, you can say is increase counter is increase counter. So if the increase counter, or you can say increase counter or increment counter is much more meaningful, you know. Increment counter. If that increment counter at that position, okay, we can say, okay, we can get is this. Get, this is counter. It's a way to prevent some weird things like this. Okay? So, this is our counter. If the counter, so once we update the counter here, I say is counter plus 1. Okay? So if the counter, after we increment that, if the counter is greater than the k number, let me now add it to the matches dot here. You know? Let me actually add it to the matches here and say, well, add the counter or add the number, add the number to that. All right, hey, this actually satisfies that, which is now this must be is greater or equal. Is the counter is greater or equal to k. Add that, and now let's going to return is the matches per se. So this algorithm is using is a n, because it's now iterating through all of these elements. Only that, we just only is checking its conditions, which actually and actually when we get this, most of the time, especially if you're using hash, you can assume that is fairly something that is using our log n or almost constant time. Okay, so the end result of our algorithm here is to be an O n log n. So if we run this, it say, hey, wrong answer, expected this. What? Didn't you update that? If the counter is greater or equal to k, matches that pushes. Okay. Oh. All right. Let me do this. Yeah, okay. Let me here is using is this. This is particularly to JavaScript object is for that. So if the dictionary number doesn't exist, dictionary counter dot set number and the 0. However, if that exists, however, if the number exists, this is what I want you to do. Okay, I want you to get that number. Okay, yeah, I want you to get that value. as our key, that we store that as our key, increment that. This dictionary counter said that the number plus whatever you got in there plus 1. So if the object here, not sure why it doesn't do that. So if the object here is equal, okay, if those numbers are equal, as a part of say, hey, I really got that. So enter here. Assuming that we only have these unique values, well, that'll be. So matches will be this. And here is so if our dictionary counter has the number, if you don't have the number, set it, okay, which is great. We're set it with the value 0. All right. If that however, if that exists, okay, if we already have that, well, I want you to now get that number, okay, get the value in your hash map, and then update that, which is something you can do here is by saying the updated value. Exactly, that's what happened. So updated counter, like so. This is the counter. Okay, this is the counter. And updated counter, which is this, or update counter plus 1. All right, this is what we're gonna use here. And if that updated counter is equal to k, please add that. And we're going to assume that we only have is one unique answer. So to me, this is quite interesting. Exactly, 1, 1, 1, and then 2. What in the F is this? Exactly, and then 2, which is that. console.log. Exactly one. This is number. This is updated counter. Oh, chill, bro. Chill. Exactly. Number, updated counter. Number, updated counter. Exactly. So now if the update counter, the number, and update counter. Oh, okay. No, this is our okay. It's because our logic when we're going to adding the elements was wrong, because we started by counting is exactly we already have them. We already have that element. So this actually going to work as expected. Yep. It actually will work as expected. Ba, 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 ba. Oh, okay. That's great. That's great. That's great. Because here we're gonna make this check after that. All right. That makes okay. 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 Exactly. So if the number does not exist, do that. However, do that and then let's go into exactly do that and then let's go into update the counter for that. And now we're going to actually check if that actually exists. All right, exactly. But he was what went wrong is that if that element doesn't exist, please add it with 0, and then is when we're going to update our counter and check if that actually, when we update our counter, we're gonna see if that actually now match here. Okay, if that updated counter not actually is the same. So we will submit this. All right. What? Wrong answer. Okay. 9 of 21 test case passes. Wait, what the French toast is this? Return the k most frequent element. That's quite interesting. So return the k most frequent element. What in the F is this? I think this is... It's because... No, not at all. Heap. Quick select, horse selection algorithm. This damaged my brain. Are we talking about the same algorithm? Okay, no problem, no problem. No problem, no problem, no problem. It's because top key frequent elements, even though the output is quite giving an integer of numbers and an integer key, return the key most frequent elements. Oh, but this represent is the oh my god. What key represents? Return the key most frequent elements. So we're saying is return the two most frequent elements here. Anyway, now let's take a look at the solution here for that. You know, it's like, what the F is this? Key free. Okay, so top key frequent elements. Okay. From NeetCode problem solution. What in the F is this one? Oh my god. Why do you do open the way you think you? This is one of the things. No, it's like this, bro. Just chill. All right. Okay.
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve top k frequent elements. I really like this problem because it's pretty clever, and once you figure it out, the code is really easy to write. So we're given an input array nums and an integer k, and we want to return the k most frequent elements that appear in the array nums. We can return the answer.
The k most frequent element. The k most frequent elements. The k most frequent element
in any order. So for example, we have this input array, 3 1s, 2 2s, and a single 3, and we want to return the two most frequent elements, right? So we know that the
we want to return is the two most frequent elements here. Okay.
Most frequent is, of course, 1. It appears 3 times, so we add a 1 to the output. The second most frequent is 2, so then we add a 2 to the output.
The most frequent elements here, or the two, assuming that we only have is unique. Okay. Assuming that we have is.
And that's all we want. Now, if k was 3, of course we'd add.
Okay, the most frequent elements in your array. Okay.
The last element. K is never going to be greater than the distinct number of elements in the input array, so that's good for us. And our input array is always going to be non-empty. So for example, for each value, right, we're going to count how many occurrences it has. So for example, 1 occurs 3 times, 2 occurs twice, and 3 occurs once. And then we can take this, basically this list of pairs, right? Then we can sort it in ascending order, right? So
we can have this, and then we can sort it in an ascending order, which is
So basically it's already sorted in ascending order, right? Because the most frequent is here, the second most frequent is here, the third most frequent is here, right? Now, of course, sorting it in the worst case, right? Basically, if every single value in here was distinct and we wanted the top k distinct values, we'd get a time complexity of n log n, right? But we don't necessarily need to sort the entire thing because we only want the top k frequent elements. So in another solution, we could actually use a max heap. So we would still do this whole operation where we count the number of occurrences of each value, and then we'd add each pair to our max heap. And the key of this max heap would, of course, be the number of occurrences, right? So the count, right? And then we'd pop from our heap exactly k times. So why is this more efficient? Well, we know popping from the heap. Well, first of all, when we initialize our heap, we're going to add this entire set, and there's a function called heapify, I think, that can do that in actually linear time, so big O of n times, so that's the good thing. And of course, we know we're only going to be popping from the heap k times. Each pop is going to take log n, and we're going to be doing that k times, right? So that's going to be k times log n, right? So that's a little bit better than n log n, at least as long as k is less than n, right? But it turns out that there's actually an even better solution. There's actually a solution that can be done in O of n time, linear time. So big O of n time and big O of n memory. But we are still going to be using this exact technique where for each value, like 1, we count the number of occurrences like 3. So this problem can actually be solved in linear time if you use the algorithm called bucket sort. So when you first think of bucket sort, this is probably what you're going to think of. The way bucket sort is usually taught is that for each value, for example, 1, we're going to take an input array, right? This is our input array. This row is the indices, the index of the array, and this is actually going to be the value. So for example, for 1, we're going to go to the index 1, and in the value, we're going to put, okay, 1 occurs exactly once. Now we're going to see a second one, we're going to say 1 occurs twice, right? Basically, we're going to go through the input array, count how many times each value occurs, and then in our input array, put that count for that index, right? Map the value to the index and then put the count of that value. So 1 occurs 3 times, 2 occurs twice, 100 in this case occurs once. Now this algorithm would be linear time if our input values, right, were bounded. For example, if we knew for a fact that every value was between 1 and 10, then we would know that the size of our input array is also going to be 10, right? But in this case, the values are unbounded, right? Like this could have been 1,000,000, and then the size of our input array would have been 1,000,000, even though the total input array size is only 6, right? We have 6 elements, but then that array where we actually store the bucket sort values is going to be unbounded, right? And also, we want the top k elements. This still isn't very clear of where exactly the top k elements are actually going to be. So in this case, this type of bucket sort doesn't work, but there's another way we can do it. So in this case, you can see for our array where we're going to be doing the bucket sort, the index, I was using each value in the input array. For example, 1 was being mapped to index 1, right? And there we were storing the count. There's actually another tricky way that you can do it that will lead us to a linear time solution. So if we're pretty clever, this is what we're going to do. For the index, we're actually going to be mapping the counts of each value. And in the values, we're actually going to have a list of which values have exactly this particular count. For example, 100, right? We know that 100 occurs 1 time. So what we're going to do is for this position 1, we're going to say, okay, this value occurs only once. 100 occurs 1 single time.
In our map.
Which value, for another value in our input array 2, we see it occurs exactly twice, right? We can count that with a hash map pretty easily. And then we'll say, okay, this value occurs twice. So in the position 2, index position 2 of our array, we're going to add that value 2. 2 is the value that occurs twice. We see a last distinct value in our input array 1. We count it occurs exactly 3 times. So in this position, index 3, we're going to say, okay, there's a value, a single value, a 1 that occurs 3 times. Now it's possible maybe we had a third 3, right? Maybe 2 occurs 3 times. In that case, we would actually have multiple values in this position, right? But in this case, we can see 1 occurs 3 times, 2 occurs twice, 100 occurs once. So they're all going to go in separate.
So they're going to go in separate bucket
positions. And then, once we've taken every single input value and counted how many times each value occurs and then put it in the appropriate spot in this array, what are we going to do? Well, we want the top k values, right? The top k values that occur most frequently, right? So what are we going to do? We're going to start at this end of the array. We want all the values that occur 6 times. Why are we stopping at
Exactly, it's because of the k time.
6 though. Why don't I extend this array farther, right? 7, 8, 100, right? Why do the indices stop at 6? Notice something about our input array. Our input array is size 6, right? So that means if every single value in the input array was the exact same, the most number of times a value could occur would be exactly 6 times. So the cool thing about this new array that we're creating is it's bounded by 6, or well, technically 6 plus 1 because we do have a 0, but that's not actually necessary. But it's proportionate to the size of the input array, right? So when we're scanning from right to left, or however we do it, we're only going to be doing we can scan through the entire thing in linear time. Now in this case, we see 6, there's no values that occur 6 times, so we can't find our top k element in that position. We'll try the same thing with 5. 5, no values occur 5 times. 4, no values occur 4 times. 3, oh, a single value. We're going to go through every value in this array. There's only a single value in this case, but we do see a 1 occurs. So to our result, we want the top k values, the top k occurring values. We are going to add a 1 to that. 1 occurs most frequently in the input array. So we add 1 to our result. We need 1 more because I think we were looking for the top 2 values. K in this case is going to be 2. So now we're going to go here. Which values occur twice? A single value, and that value is 2. So we're going to add that to our output array. So now we've gotten the top 2 values, and then we can return this array. Now, why is this linear time again? Because remember, the max size that this array could possibly be is going to be about equal to the size of the input array, right? Because we could have a value, for example, 1 could occur 6 times. In that case, we'd have 1 over here. Now, what if every single value in the input array was distinct, right? That's another extreme. What if we had 1, 2, 3, 4, 5, 6? In that case, this position would be empty because no values occur 6 times, no values occur 5 times, 4 times, 3 times, or 2 times. Every one of these 6 values would go in this position at index 1. Reason being, each one of these occurs exactly once. So in that case, we'll have all 6 values concentrated over here. And that's still going to be linear time because, yes, we are going to be iterating through this entire input array, which is going to be big O of n, and then we're going to add another big O of n to that, right? Big O of n plus big O of n, because we're going to have to iterate through 6 values in exactly 1 position. So that's still technically linear time. Now we are creating this array to help us, and we're also going to be needing a hash map to count the occurrences of each value in the input array. So the memory complexity is also going to be big O of n.
That's pretty, bro. Oh my god. That was something I was thinking, is because, yes, because in my hash map, I'm counting all of the number here, okay? And I have this, the big O of notation of my memory is ON, because this will be I'm adding all of these elements and counting all of these elements, and I need to iterate through all of these elements based on the length of that. The funny thing is that, alright, at the end of the day, I will need to have a way to count them, okay? To count those, and once I count that here, I want to know which one of them are the top k most repeated elements. So how many times one of these elements repeat 1 time? I want to know the number of occurrence of all of these numbers. I want to know if the number of occurrence k on this entire list. If you have an array where your now count is the number, the counter number and your index, and if your value will be is all of the time that you have counted that, okay? Hey, how many times you count this in an index? In the index 1, I count all of these elements. How many times you count 3 times? How many times you count 3 times? How many times you count 3 of these numbers? This one.
With that being said, let's jump into the linear time code. It's pretty easy once you can identify this trick. So we are going to use a hash map to count the occurrences of each value, or also the array, the special array that's going to be the same size as the input array is going to be called frequency. Basically, the index is going to be the frequency of an element or the count of an element, and the value is just going to be the list of values that occurred that particular many number of times. So I'm going to have I'm going to initialize this as an empty array. The number of empty arrays that go in this is going to be about the size of our input plus 1. So now I'm just going to go through every value in nums and just count how many times it occurs. So for count of this particular n value, we're going to do 1 plus what its current count is, count.get n. Now if n doesn't already exist in our hash map or dictionary, we're just going to put a default value of 0. So this will return 0 if it doesn't exist. But this is how we're going to be counting the number of times each value in nums occurs. Next, we're going to be going through each value that we counted. So n, c, in count.items, because that's going to return the key value pair, every single key value pair that we added to our dictionary. And for every key value pair, for every number and count, I want to change in the frequency array, I want to insert. So for this part,
exactly, the frequency array, I want to know that I'm iterating through the count item. That I actually have the count in my index. I'm gonna put is the number of time that I count this, followed by the values there.
Particular count, remember the count is what's going to be the index. So at index count, we're going to append to that list this value n. What we're saying is this value n occurs exactly c number of times. And once we've done this, we basically
exactly this value of n, this value number here occurs exactly this value n occurs number of c times in our index.
Basically initialize everything we need to. So now we're going to have our result output, right? We want the top k elements. So so we're going to be iterating through this array frequency in descending order, right? Because we want to start with the numbers that occur most frequently. So for I in range, length of frequency -1, which is the last index, and we're going to go all the way up until 0, and we're going to be going in descending order. So we're going to put a -1.
That's one of the lovely things of Python.
As the decrementer. And we're going to go through every value. So for every, let's say, n value in frequency at this index I, because we know everything inserted in I is actually another sublist. So it could be empty or it could have some values, whatever it does. So let's say n is non-empty. Then we're going to go ahead and take that n value and append it to our result, because we're basically getting the n value that occurs most frequently. Now, when are we going to stop? At some point, our result output is going to be the exact same size as k, because we're guaranteed to have at least k values in our input array. So once that happens, if the length of result is matching exactly k, that's when we can go ahead and return result. We know this is guaranteed to execute at some point, so we don't have to put a return statement outside of the loop, and that is the entire code. So we could have solved this problem in decent time if we used a heap. It wouldn't be too bad, k log n. I think that's a doable solution, but with this kind of neat trick, we can do this in big O of n time. And I hope that you did learn something, maybe a little bit about bucket sort. This problem definitely taught me something when I first solved it. And I know many people have been requesting problems, and I'm trying to get to all those requested problems.
Holy, that's a very interesting way. That was 3 years ago. This was a very interesting way to solve real-life problem, especially using the combo to solve a specific real-life problem using counter, exactly, using counter, okay, That was very interesting way to solve a specific real life problem. Oh my god. Mm-hmm. By counting and work exactly by counting and working with hash and array as a way, yeah, by counting and working by counting and working with hash and array as a way to identify most common identify most most frequent element, most frequent elements. I'm a most frequent elements. It is useful. Okay, most frequent elements here. The most frequent elements here. This can be useful for this can be useful for business handling inventory. This can be useful for small to big business handling inventory, or when you need to pack up your stuff to travel. Holy moly. Okay. Well, that'll be all for this video. Take care. Bye bye.